Welcome back. So in our last lecture we have discussed how processor architecture is made inside a stored program control, that is our SPC exchange. So let us discuss one example with respect to processor architecture inside an SPC exchange. So in this example let us consider a SPC switching system which has two central processors. Right now they have defined the number of central processors in this exchange is 2. So it set up all connections. Normally the load is shared evenly between them. Means load is shared between those two central processors. However, if one fails, the other handles all the traffic. So that is what they have defined. If any one of the one processor is going fail, so the other processor will be handling all the traffic that is offered for this particular SPC exchange. So during the busy hour, the total traffic offered to the exchange is 1000 Erlang. So that is what during the busy hour 1000 Erlang traffic is applied for an SPC exchange, and the average holding time of call is 3 minutes. So that means H is given, average holding time H is given as 3 minutes inside a busy hour, and the processing times for calls can be assumed to have an exponential distribution. Of course, that is what it is, with a mean time of 162 millisecond. So it is given that in order to process a particular call, so the SPC exchange needs a mean time of 162 milliseconds. And now we want to find the percentage of tasks which must queue for processing during the busy hour when both processors are operating. So we have to find the what percentage of tasks are going into the queue when so many number of certain amount of traffic is offered for an SPC exchange during the busy hour, and with the condition that both processors are operating or both processors are sharing the load. Similarly, we have to find the percentage of tasks which must queue for processing during the busy hour when only one processor is working, that means when one processor is out of service. And also what will happen if the number of calls offered to the exchange during the busy hour increases by 25% when one processor is out of service. So what will happen for a SPC exchange when calls offered to an exchange during that particular busy hour is increased by 25%? Of course, right now the condition is only one processor is working and the other processor is out of service. So we are having three cases in which both processors are operating fine, in which only one processor is operating, and here only one processor is operating, but what we are doing is we are increasing the load offered for an exchange by 25%. So now in this case what is the probability of delay observed, or what is the number of calls offered to the exchange observing busy? So we have to calculate, or probability of delay must be calculated in all three different conditions or cases. So in order to calculate the probability of delay, first let us calculate what is the number of calls that are arriving during the busy hour. So it is given that the exchange is offered with 1000 Erlang of traffic, and we know offered traffic A is given by CH by T, and A is given as 1000 Erlang, and C we have to calculate, and H is given as 3 minutes. So 3 minutes of holding time for each call, and also we are dealing with a busy hour, so it is about 60 minutes. So if we calculate the number of calls that are arriving inside the busy hour will be obtained as 20,000 number of calls, that is per busy, that is per hour, that means inside the busy hour. And next let us calculate what will be the traffic offered to each and every processor. So please note that there are two processors available with an SPC exchange, and we want to calculate what will be the traffic offered for each and every processor. So when I am calculating the traffic offered for each processor, so same equation, A equals CH by T, and right now C number of calls is 20,000 and H the holding time of a processor in processing a particular call is given. H is given as 162 millisecond, of course, so that is given. So processing time, that is mean time call processing, is 162 millisecond. So if I substitute, and the total duration, if this is in seconds, so 3600 seconds for a particular 1 hour busy hour. So if I substitute, so we are going to end up with 0.9 Erlang. So offered traffic for each processor was obtained to be 0.9 Erlang. So with respect to first case, we know we want to calculate probability of delay. So for calculating probability of delay, so we know for calculating probability of delay we need P of 0. So we know from second Erlang distribution, so 1 by P of 0 is given by this equation. So if I substitute n, so right now there are two processors involved with respect to each exchange, or with respect to our particular SPC exchange. So two processor means we can assume it as two trunks or two servers. So we know n is number of servers in this particular equation. Similarly, two processors are involved in handling the offer traffic. So what we consider is n is assumed as 2. So if I substitute n as 2, x varying from 0 to 2 minus 1, which is 1, a power x by x factorial plus 2 into a square by 2 factorial 2 minus a. So we know what is a for a particular processor, and also we know what is n. So with this I can calculate 1 by P of 0 to be equal to 2.64, and P of 0 can be written as 1 by 2.64. So now we will use this P of 0 in our standard equation, that is probability of delay observed by an queuing system. So the probability of delay observed P of d is given as a power n by n factorial n by n minus a into P of 0. And of course we know probability of delay is nothing but grade of service of queuing system. Grade of service of queuing system. Of course all SPC exchanges are nothing but a queuing system. So probability of delay is E2, n of a, which defines the grade of service of queuing system. So right now n is known for us. There are two processors, so n is 2. So if I substitute in this equation n as 2 and a as 0.9 Erlang, so then we will end up with e of 2 of a equals this, and we know what is P of 0, and if I substitute those things I will end up with probability of delay to be equal to 0.279. It implies that 27.9% of tasks are moved into queue when SPC exchange is processing the calls with two number of processors. Is it clear? So 27.9% of calls are tasks. Task means, of course, you can assume the number of calls also. Tasks are moving into queue for processing. So let us consider the second scenario in which only one processor is working. So if only one processor is working, then n is going to become 1. N will be equal to 1 because the other processor is out of service. And we know the probability of delay observed by a queuing system is given by this equation, and of course it is e of 2, n of a. And if I substitute what is n equal to 1, and if only one server or only one processor is involved in taking the entire load of 0.9 Erlang, then we can directly write property of delay to be equal to E2, 1 of A is exactly equal to offered traffic for each processor or particular exchange, or instead of saying exchange we can call it as a processor. So, and of course that is known for us, it is 0.9. so it implies that when only one processor is working and the other one is out of service, then about 90% of tasks are moving into queue for processing. So let us consider the next case in which we are increasing the offer traffic for the particular exchange. That is about 25% is increase and only one processor is working. So in such case we can directly calculate the offered traffic or offered load for a particular processor to be 0.9 into 1.25. so previously with only one processor, and previously with respect to previous load it was just one. Now we have increased it by 25%, so 1.25 must be multiplied with the traffic offered for a particular processor. So and we can obtain the new or the only one processor which is working fine. When we increase by 25%, so it will be 1.125. so this is what the offered load for a particular processor which is operating. So in such case, since this A offered traffic for a particular server or a particular processor should be always less than 1, since it is greater than 1, so it is clear that so more than 1 Erlang is offered to a single server, so the queue length increases continuously and the system is going to crash. So since the offer traffic is greater than 1, so the queue length is going to increase continuously and the system is going to crash. And please don't forget to mention these comments once you calculate the required results. So as we have shown here, and also we have shown here with respect to all three different cases.